Thank you very much for the introduction. My great pleasure to be here again in Miami. And okay, today I talk about the chemostat model with time dependent delay. And this is a joint work with my collaborator, Professor Teresa Faria from the University of Lisboa in Portugal. And first, we can know that we have a very different type of audience here. I will try to give some motivation for why to investigate this type of equation that's called delay equation. And then I will enter the problem. So I will try to be not too technical in order to bring it for you some motivation. But some part, unfortunately, I will need to be a little technical. So then just to explain a little, I will start with a very simple model, the logistic equation, that's the population model. And as you know probably very well, we have that the logistic equation is given by this model that appears here, and it was introduced by Gerlos. And after that, we have that Hudson was one of the first that started to realize that it was missing something in this model. Because if you see, when we think about population model, there is a time between the verb and enter in the migration process. And this time needs to be in the model in order to have a more precise description of the population model. Then, if you see here, it's very similar what we have for the logistic equation that probably you all know. But it has here this pole that appears that is this time between verb and migration process. So we would like to describe that in the equation in order to bring more precision for that. However, if you look, it seems very simple to have this pole that appears, but this small pole makes a lot of difference in the behavior of our solution. So here you can see how this small delay can provoke a lot of oscillation in your solution, so in the behavior of your solution. If you remember, when we have the solution of the logistic equation, we have something like that. And then here we have a lot of oscillation that's provoked by this delay term that appears there. So, but later, I don't know. Okay, come back. Later they found out that this delay was in a wrong part, because if you come back here and try to see the model, you will see that if you consider that B in this case bigger than 0 are both in common, what you have is that the delay appears in the negative part. And that here is referred to the death rate, not the birth rate. So they realized that, and then they improved the equation, the model that was proposed by Hudson. And since they made a lot of experiments with a rho-phi population, this equation is called the rho-phi equation. So here we have now the delay in the correct part. But again, with the delay, we still have the oscillation behavior of the solution. So we have the solution is very oscillatory. So here it's considering the delay equal to, and the second one is considering the delay equal to. So in all cases, you can see that the solution is oscillatory. So we have that the delay can do that. So can change a lot the behavior of your solution. So you can see it's somehow very similar what we have for the logistic equation, but the behavior is totally different because of this delay. So, but then later, maybe realize that okay, this is nice, but the delay in the equation. However, if you see the time between verb and enter the maturation process is not constant, but it should be different. It should depend on other things, not be constant for all species and for all populations. And then they realized that it would be really important to consider state-dependent delay, which means that the delay now depends on the state. So this brings much more complexity for our model, but it's really important in order to bring this precision for the model. So here, they realized that some population of seal and whales, and then they realized that this was not constant, the time between birth and migration process. So they brought this model that you can see here, and now our tau is a function of the state. So it depends on the state. So now our delay is a state-dependent delay. So we have this function. But this brings a lot of complications when you try to work directly with this type of problem, because here you have your x is composed with tau and then with x again. So if your x is, for example, not continuous function, so you have a lot of problems to deal with that, because, for example, if you have your x, the regulated function that the electroregulated exists only, you have the decomposition of the two regulated functions is not always a regulated function. So you really need to deal here with some problems in this situation where you do that composition. But here again, you can see that even in the state-dependent delays, we have this oscillatory behavior of the solution. So here, the state-dependent delay is looking at the interval here from 2 to 20, and then we have exactly this oscillatory behavior for the solution. And somehow we can also compare to see, okay, but it works or not work to consider state-dependent delay. It's really hard to deal with that because of regularity, because of the behavior of the solution. And then here you can see, for example, in this specific case, if you consider your constant delay equal 40, it's almost the same to consider state-dependent delay. So in this case, this one does not work to consider state-dependent delay because it's much more complicated. But in most of cases, it works to consider because it also can change a lot when you consider state-dependent delay instead of constant delay. Sometimes you can have like stability for the constant delay, and then if you consider like a time-dependent delay or state-dependent delay, you can do the stability of your solution. So it's really important to consider it depending on the case. So here is on the timeline to resume about the evolution of delay equation. So if we try to see how it was in the timeline, we have that the first investigation in that direction started with Marquez de Condorcet. And Marquez de Condorcet actually was investigating about part of the differential equation. And he arrived at a type of delay because there is a very close relation between partial differential equations and delayed differential equations. It's possible to write some partial differential equation as delayed differential equation. And also you can have some relation between them. And here he was investigating about partial differential equations, and accidentally he arrived in a system of delay equations, and he started with the new techniques to solve this type of problem. Then later we have Poisson, and also Poisson worked with delay differential equation, but again, not directly. He was working with other types of equations, and then he achieved the delay differential equation, and again started some new techniques for this type of equation. But then Victor Volterra was one of the first to bring the importance to considering a model described by delay differential equation. He brought the importance to consider the time between cause and effect, and also the importance that the influence of the past has in the behavior of your solution in the moment, in the present. So Volterra brought mainly about that, and he started with some many models about the delay differential equation. Then we have Charles Picard. Charles Picard was the plenary speaker of IPM in 1906. And in his plenary talk, he also mentioned about the importance to consider the delay differential equation in order to describe many phenomena. However, he brings about the difficulties behind in order to have to treat those equations. And then, okay, as I mentioned before, we have Hutsu that brought that model of population that also has delay, and it was one of the first models of population with delays. And then we have also the three Brazilians, also Newton, and that's improved the model bringing with the correct part. As you see, in the Hudson model, the delay appears in the death rate, and it should be in the birth rate. So they brought a better approach for the model. So only to finish the introduction part about some motivations for the delay equation, I will bring some applications only to see that it's not only population model, but yeah, the delay equation are really important for many different types of models. So first, I think this is very nice, this one, because we are now speaking a lot about artificial intelligence, and then here, yeah, the delay equations are really important for that. Because when we think about artificial intelligence, what we have behind that is processing data. And in order to process some data, you take some time to have this processing data. For example, if you would like to be very fast in your work, and if you open many things in your computer, let's say Word, LaTeX, and PDF, and all the Firefox, you will see that in your computer will be slowly because it will try processing all those information. And it's really important to understand that this time to processing will depend how many quantities you are giving to your computer processing. And here is exactly that explained that this time, the delay will depend on these things. So here in this paper, you have the user, and it sends some information that you have this line, let's say, of information to be processing, and it will take time. And this time will depend on the time of this line of information that are depending for your computer to process it. And then after the processing, it comes back to the user with the information that the user has. So if you see here, we have exactly that. You have that the delay is really important, and we have a type of state dependent delay. So this you can see more details in that paper that is was published by Paula and Christine in this journal. So also there are some other types of models that you can see about proliferation of a cancer cell. That again, it's really important to consider the delay. And here we need like partial differential equations with delay. Usually the models for the cancer cell, the population of cancer cell, are described by CD. But if you know that the proliferation will depend on the stage of the cancer, again, it's a type of delay that depends on the stage. So here again, it's really important for that. And there are many works in that direction that you can see many models for the proliferation of cancer cells. And here also about the technology, we were in the past with the pandemics about COVID-19. And we know that this type of disease has an incubation period, which means that if you are infected with COVID-19, it takes some time in order to the symptoms appear. So nobody knows that you are infected because you have no symptoms, but sometimes it's time until the symptoms appears, and this time it can be viewed in the model as a delay. And again, the delay is not constant; it depends on other factors. We know that someone can be infected and the symptoms appear almost immediately, but others take a lot of time. So we have some in between. So here we have that many interesting models appeared in that time of COVID-19 using delay differential equation. And not only for COVID-19, but all the disease that have this incubation period, like fever, unique dengue among. So here again, talking about the type of disease with information. Okay. So this is only to bring you some ideas how it's really important to consider this type of delay agent, the motivation. But now I will focus a little with my work and it will be a little technical, sorry about that, but I will try to escape as much as I can from the techniques, okay? Only to bring some ideas behind, only to see how we can deal with that. So here, just to explain first, our model is the type of chemostat that tries to simulate the nature environment. So we are trying to understand the behavior of some microorganisms about this reproduction and how it works, and then we try to simulate in this chemostat the nature environment. And then here is our model. So this type of model was investigated about chemostat, was investigated by the main authors. However, we have no one that brings time-dependent delays. So here we brought the time-dependent delay and also other things like here we have our D is depends on the time, and we have the others like constant. So we have some differences in this way. We have no one that has the time dependent delay. And then here, so we have this type of model. It seems a little complicated, but we will see that we could extract several important information from that. Here, I want to explain a little about our variables that we are working. So our S0 will be the initial concentration of this substrate that we would like to investigate about the microorganism. And then also we have the DT is the rate of the inputs of our nutrients in the environment that we are creating here. And this FOC is the concentration of the substrate. So it's the thing that we really want to know what is happening here. And here, one thing that's really important about the delay, and the delay is exactly the time of our cell type. So it's really important here to understand in order to see that usually it's not constant. So it's really important to consider one general type of delay. So here is our model. And also we have some technical hypotheses. I will not answer very much of that, but only to bring some explanation here. So usually this type of modeling works with some specific PI, but in our case, the PI are more general and that can also include all those types. So here you see our PI is a non-decreasing and globally link shift function. So we have more general type of hypothesis in order to include more different types. And also here we have some hypotheses concerning our delay. And here you can see we need that our delay is differentiable because if you see it appears in our model the derivative of this time dependent delay. Okay, so here are the other hypotheses that are technical, and here we work with some continuous function in this specific case. But I will also mention that later that we are trying to prove that to have not only continuous function but also regulated function. But until now, what we work with continuous function. So here, I want to mention that one of the first things that we try to do is to take our model and make it easier. Like I try to do some relation between this model and one type of OP and divide that in order to only deal with the OP then with this type of equation. So first, we will try to see if we can have a type of OP that we can also read with the CPDs this equation. So here first, we can have that our concentration VI given by this here, and then doing some of the difference between VI and the XI that we had before. And then here the difference between time. So T and the initial one, initial time. We have these, we have these inequalities here, and also about our F is also integrating our equation before it here. If we integrate this first equation here, we will have exactly this for X. So, and then if we try to come back, you can, using both definitions, you can come back to our system before. So if you do the derivative and come back, you're back to our equation. So we have this relation between these two things. And then here, we are dealing with a bounded function. So we have that the supreme like this, the equal like this, and then we deal with some notation that appears here. So I don't have the only to mention because it's still here. So here we have this F bar above, it will be the supreme, and the F bar below will be the equal function. And since we're dealing with bounded function, they are well defined. And also we have the others here concerning our concentration and also concerning the D and so on, and also about our time dependent delay. We also have the boundness, and we have this. So here, as I mentioned, we worked with the continuous function space. But are very usual to have. So here is this and more, and that is here. And here also it's important to mention that we use very often this notation when you deal with functional differential equation that is this x and this t, yeah, we don't know, but this means not the partial derivative, but it means that x t theta is equal x t plus t. And it's really important to try to rewrite our model in this way using this notation because we have a huge return about the results for this equation. As you can see, x dot t equals f t f t. So if we try to use that in our hypothesis in a classical one, we can like have a lot of results that we can use for our problem. So the idea is also to try to read our problem in this way here. So, and it's possible, we will see that we will be able to rewrite in that way. And then here also will be our initial condition that we will define in this way. So it's only just to bring it, and also just to mention that we will use this notation here to be the solution of our problem, the functional one, with the initial condition and the function parting. So if we have that, that notation will be all the solutions. And since we're dealing with a model that has some meaning about population, and we want to understand about the microorganisms, we needed to define how would be the best choice for our initial condition, like this case, the appropriate state to look for our initial condition. So here, since we're dealing with a continuous function, our states will be all the positive ones in the beginning and the time zero. We are assuming that we are dealing with the positive condition. Okay, so here is the test of all those functions. Okay. And also, we would like that our solution be positively invariant, which means if it starts positive, it continues positive. And it's very important to us because we are dealing again with a population model, so we need to have that type of invariance. So we start with this initial condition with some facts, and we continue with the solution that facts, which will bring to us the positive solutions. And then, okay, we have some direct results in that direction. So here that ensures that the two facts that we started, that we look for our initial condition, they are totally invariant for our equation. So, okay. And also that we have that our solutions are all defined for all the iterations. And now, as I mentioned before, one of our goals is to try to rewrite our model, our equation, in a more simple way, in order to deal with these more easier equation, that's the OD that you can see here. So the next idea of this lemon here is to prove that if we define our y in this way, where f and xy is the one that appears in our main equation, what we have is that y is the positive solution of this OD. And it's a very easy OD to treat. So if we have this relation, it will be very easy because from this OD, we can have the information concerning f of t and fi. So it will be very easy to do that because we have this relation. So here we try to do that, and it's only calculations. Here is the proof. I will only pass very quickly on not to bother a lot with any calculation. But here you have your equation, and then what we do, we have the definition of this y, and what we do with the derivative for both sides, and we use the definition of our problem. So we have the first one from the F, here we know what happens with the derivative is one of our equations, and the second one again we use the information of our system. And then we have these inequalities that a lot of calculation doing the problem, derivative, and so on, and using the information of our system. And then we can do simplification and more calculation. And then we achieve exactly the equation. So here we now can see that we can deal with an opening as to deal with the delay differential equation in order to bring some information. It needs to be very important to us that. So, and then also, if you come back, since we have here this only in 5, we know how to solve that. It's developing very easy to know the expression of our solution. So here is exactly what we do. So here is the expression for the solution of our problem. And then using the hypothesis, we can find some upper bound and lower bound for our y. And then we will check that our system that we had before is definitive, which means that there is a uniform upper bound for all solutions. So here we have this information. And also we have that for our non-negative solutions for our case, S of t and x the variable state of our problem. So as I mentioned before, exactly that we have that the first equation, and then we could relate it with an OT that's very easy to do. So then we can bring all those information to the other side. So here also again, it shows that if we have two different solutions, and then as we know, that's the solution of our OD, and if you do the difference between them, what will happen here, and if you define this y of t equal the difference between the two solutions, if you use the definition, you will see that it will be exactly this y, the derivative of w will be exactly equal that. That's the no bigger than, very easy, and then we know how to calculate it. And it's easy to calculate the limits when it goes to infinity and goes to zero. And okay, here is only to simplify the notation. And as I mentioned before, okay, one of the goals was to have the relation between our equation and an OD. And now the other thing that we want to have is some way to rewrite this equation in a form that we can use no results for functional differential equation here. So in order to do that, we needed to rewrite our equation in that formula that appears in 9 here. Because here, if you see, if we know something for this type of equation, it would be nice because we have a huge literature about many classical results for that. So we are trying to rewrite in this form and more. We can also apply for our model and not only for many other models that fits here. So that's why it's better if we can rewrite in this way. So the idea is to rewrite in that way, and in our case, it's possible, but our FI will be a little let's say, we'll begin the kind of this in here, but if I is this expression here. So it would be a lot of population, but we can achieve that, and also we can see some possibilities for the hypothesis for this F that are like a theoretical hypothesis. And then we have that we can do with this type of problem. So other things actually, because we can get that problem, I will not answer all of them, but I will mention one more that's in one chapter, but also we worked about periodicity of solutions. We tried finding properties for our solution. But here I will only mention a little about the global chapter because to have a very important interpretation for our case. And here we would say that a non-negative solution, that's fine, that we write this way, will be called a global attractor if you use blue. The limit with n solution and the b solution, it goes to 0 when t goes to infinity. So when we have that, we say that this non-negative solution is a global attractor. And we will say that it's globally asymptotically stable if it's stable and globally attractive. And here I want to mention that in our case, we understood that globally attractive would be exactly if we have any solution with initial conditions is 0 plus is a global attractor that we mentioned. And why this will be very interesting here is because we will see here in that case, if we consider this type of solution, let's say FT000, all the ones for 0, we have that in F of T is a solution of the OP that is given by 5, the one that was rated for Y that we solved for. So we have that B with X in the first variable in the order 0 will also be a solution for our problem. But here you can see what's happening with the solution. All the rest are 0. And then what happens is that with this type of solution, the global attractor, which means the biological sense, is that our population will go for the extinction. So it will disappear. So here, that's why we are very interested about this to understand in which condition our population will be. Right? So here are some hypotheses in order to ensure that our population will be. So here, if we consider all those hypotheses, and then here Y has will be the solution of 5. What we have is that if the limit is more than 0, then what we have is that any washout solution of our problem is a global attractor of all non-negative solutions. So using that, we have some conditions in order to ensure that our population will be extinct. Somehow that we can be. So, okay, I would like also to mention that this was one of the first that worked that direction in order to try to have more sophisticated delay this type of problem because I mentioned before, like it was this type of problem that was dedicated by many people. But using this type of model that we have, and using the time-dependent delay, we have another case actually exactly the model that we have here. We don't have the one with time-dependent delay. But also we would like to investigate something more general because, okay, time-dependent delays are nice, and also they have a better description of the model. However, state-dependent delays would be much more interesting, but it's really hard to have the independent delay. Because if you see before, it appears in our model the derivative of the time-dependent delay. And if we use the state-dependent delay, we will appear the derivative of the state-dependent delay. And this will be like very hard because it will appear like your solution again, derivative both sides, so you have much more complication, much isolated the part that you have derivative. But it would be really interesting to see how it behaves when you have the state-dependent delay. But it's something that we are trying to see how we can overcome that appears naturally by the state-dependent delay. And also here you can see we work with a continuous function. And we are very interested to see if it's possible to generalize not only for a continuous function, but let's say for regulated function that is only the natural limit exists. So it would be really nice to see what happens in that case that we have this type of solution, let's say not only continuous solution, but a regulated solution. However, again, here the difficulty is that you need to compose regulated function, and if you compose two regulated functions, you cannot be sure that the composition is regulated. And this gives a lot of problems about the regularity of our function, our solution. So it's something also that we need to think about. And the other type of problem that we have, you can see here, we consider that our delay is bounded. And the other question is what happens if your delay is unbounded? Of course, it's much more complicated again because the new phase is much more hard to do, but something very interesting that should be basically what's happening in that case that you have unbounded delay. Because here, as you saw before, we have the hypothesis that our delay is bounded. So it would be interesting to think how could we do that. So there are many open questions in the case of a chemostat, and also we can have more sophisticated types of delivery. Time-dependent and space-dependent delay at the same time is also possible. So there are many possibilities on that. And also only to mention that about the delay equations, also we can have many different types of problems, as I mentioned before. Especially now with the artificial intelligence, there are some interesting models to think how to work with them. Yeah, it's sometimes it's difficult to have to work with the because we have some difficulties that we do not have when we deal with all these. But also it's very interesting to see this type of model to see the precision, more precision that you can get when we apply